take this version 5.08 and unpack the box and make it run. So I don't have too much of details. So I just took the slides from Roberto Padilla from NCEP, from the course we did 2 years ago. So it didn't change much. So you will see how the files are organized in different folders. What I want to talk to you here is how things are organized in terms of the different steps for running the model. And so the WaveWatch code and executables, actually several of them. So I guess many of you know about that, but not people have never run WaveWatch. And all these different programs comes with some input files and they produce some outputs. That's the basic idea. So there's 4 or 5 main steps in running the wave model. So first you need to define your model settings, the symmetry, the shape, the resolution, the time step, the parameters. All this is done by this grid preprocessor, which essentially will define the parameters for your configuration. And it is done by a program which is called WW3_grid. And all the WaveWatch programs, or most of them, have a name like that, WW3_something. So the grid preprocessor will take some information about the symmetry and everything and produce some binary files that will then be used by the other steps. The next step typically maybe to define some initial conditions. Actually, very often we don't care about initial conditions. We just start 7 days before, and then the waves spin up. And in the Atlantic, maybe 5 days is enough. In the Pacific, you need at least 2 weeks to get the swell to travel across the Pacific. If you do the Mediterranean, in 3 days you get the spin up, which is good enough. So very often we don't care about the initial conditions. Another step, if you're only running a small piece of the ocean, is to define the boundary conditions that will come into your domain. So this is new in version 4. And of course, it's in version 5. You can define your boundary conditions from spectra, which have been produced by another model run. And so these spectra, you can take them either from our database, which are part of our hindcast, and this is part of this FTP I was showing you before. You can use also the spectra from NCEP. And there's 2 programs you can use. So you have either this one for spectra in ASCII, which are still, I think, used at NCEP, and we completely went from ASCII to NetDF. So there's another flavor of the same program called BOUNC for NetDF. And essentially, that will take some spectra in NetDF and produce a proper file for forcing your coastal model. Then, typically, there is some forcing you need to provide to the wave model. And the forcing can be the winds, the currents, the ice concentration. We also have now the iceberg masking, the water level. And all these fields are used at runtime. They use flat binary files to make it faster for running it. So if you have NetCDF files for forcing, you need to pre-process the NetCDF into these binary files so that the model runs with that. One interesting thing is that the forcing, because it's a flat binary file, you can actually still, you don't need to wait until the full file is finished to start running. And this is what they do at NCEP. They start running the wave model right after the atmospheric model. They don't wait until the end of the atmospheric model. And so every 6 hours of the atmospheric forecast, they write the wind to the disk, and then they pre-process it and add it to the forcing file. And so the WaveWatch just waits to get the wind fields, and so it's running almost at the same time as the atmosphere. And I do that, for example, for the tidal current, because I have 1 gigabyte of tidal currents 1 year, and the pre-processing can take sometimes 1 hour. And I don't want to wait 1 hour to start the launch, so I just start the pre-processing, and so it does that, and so my model starts running, and the file with the water levels and currents from the tide is still being updated. Okay, that's the model input. Then the actual running the model, integrating the wave action equation in time, is done by 2 programs. If you have only one grid, you can use the old, and this is what we still do, way of doing it, which uses the ww3_shell. And it's called shell because it's, it goes back to the WaveWatt1, which was Hendrik's thesis, and actually WaveWatt stands for wave, watt level, and current hindcasting. So Hendrik, during his PhD, was doing a couple model with storm surges. So the shell was actually just a shell calling the wave model, the storm surge model, and all that stuff. So shell will call the integration of the wave action in time and all that stuff. This is for one grid, and this is also what we use for coupling with the Meso-NH and Mars 3D on tomorrow or Wednesday or Thursday. Yeah. So when we do the coupling, we'll use also W3 shell. The other option, if you want to use multiple grids communicating in two ways at the same time with triangles or squares, whatever, it's another program called WW3Multi, which essentially will call the same routine, but for each different grid separately. When these two have run, you get results, which are a nice set of binary files that you cannot read. And so then typically you need to post-process these binary files into something readable. It used to be all in ASCII, and so actually we haven't used these two for a long, long time. And so the one we're using, there's a mistake. It's not NC-OUTF, it's called W3OUNF for the field output and OUNT for the point output. And Mikael, is that the PDF or is that the? Okay, so you have to correct that. There's also some programs for making some plots using the GRAD system from NTEP and CAR, and we have never used it here, so or almost never. So I'm not going to tell you much about it. Sometimes you may want to put all the grids together to get one single grid, and this is done with WW3dint, so grid integration. And this one is for running the model with automatic domain decomposition. Essentially, it's a wrapper to be able to run WW3Multi, but it's doing the for domain decomposition. This was new in version 4. All right, so each of these programs is reading information input from a file which has the same name, but with extension .inp for input. So for example, WW3 grid is going to read its instruction from WW3 grid.inp. And these files are really kludgy and funny and trying to work with, so I apologize for that. But we're slowly changing that to just making name lists. So this is what Mikael is going to do this summer, to convert the WW3Multi to only full name lists. Right now, the issue with these files is that they have a specific order, and so it's a text file, and WaveWatt expects to find the information in a given order. And so if you don't give the information in the right order, it will give you, at best, understandable error message, which to you may sound like an ununderstandable error message, and then you just send an email and ask us what's going on here. So hopefully that will be solved soon, but right now you have to be careful about the order and what's going on into this grid.inp file. Especially nasty is this one, because we have added so many different options that the actual order of the information can change with the options of the model, and then you get crazy. For most users, you never run into this, but if you want to use information on the bottom roughness coming from grain sizes, or if you want to use some funny ice stuff, there's some extra lines you have to put, and it's a mess. So that will change soon, but right now you just have to be a bit patient with that. In general, you can put some comments in these files, and so I advise you to use the version of these files. There's some template for these files which are contained in the INP directory, just next to the FTN directory. And you will see some examples with all the comments. Of course, with all the comments, the file is very big, very big. And so Hendrik, in many of these test cases, just removed all the comments, but then you don't understand anything. And the comments are defined by a character, which is usually with a $sign, but actually it's the first character of the file. So the first character of the file defines what should be the comment. Right, so if you start with a hash, it's going to be hash for the comments. But I don't know why he did that. I guess, yeah. Just use dollars, please, so everybody will use the same. Yeah, and all these programs will write some output telling, hello, I'm happy, I'm doing this and this and that, the standard output. So what we usually do is to redirect the standard output to some output file. And usually what we do is to send that to www3grid.out instead of INP. And the good reason for doing that is then you have some trace of what's going on when you run these programs. Otherwise, you just have it displayed on the screen, then of course it appears. And so the standard output will essentially tell you what all the steps that are going on. But of course, the most important part is the binary files which are written as a result of that. And these files have extensions starting with www3. So typically, you'll get moddef.ww3, which is a model definition file, which is a result of this www3 grid. Except for when you're running with multi-grid, instead of having the extension .ww3, you have an extension which is the name of the grid. So each grid will have a name. You will get a .atlantic or .global or whatever you want. All right. So the model definition, which will be produced by W3 grid. So the result will be this moddef.ww3. And this file will contain the bathymetry information. Yeah, there's also some subgrid masking, like just small island smaller than the grid. There's some information of how much energy is fixed, stuff like that. The masks, the land sea masks, the other information. All the parameter settings for the different parameterizations, so the beta max I was talking about, the all the other numbers, they're all stored in this moddef file. And that's, yeah, the time steps, the position and location of the input boundary points for the nesting, and all that. And also, yeah, the position of the output boundary points if you want to nest one grid with another. Okay, I said that already. Okay, so that's the logic, the flow chart. So you have this executable file, W3 grid. It's going to read the instructions from this file. It's going to probably, in this file, will tell it, okay, you have to read the bathymetry from that other file and the mass from that other file. So yeah, you have some other files with that information. It will ingest all that and produce this moddef.w3. We will have some tutorials on how to generate these information from standard things like eTopo or other sources, GSH shorelines, and what have you. And so we'll do that today or tomorrow. And so typically you run this program only once, and then you will use that very often each time you run the model with the same configuration. All right, the initial conditions is about the same story. This is only used for test cases or academic cases, which you have some special things. If you want to start with some uniform t-state, you want to start from 0, you want to start from a John-Swap parameter, whatever. So you define these options in this strT input file. You run this strT, and it will create this restart.w3 file. This file typically contains all the spectra on the entire grid, so it can be a pretty big file. And if you don't have this file when you run the model itself, you get a warning error message telling you, oh, we don't have a restart file, but the model will still run starting from 0, no waves, and just starting to generate the wave from the wind. Typically, what we do in our forecast system is that we use the we write restarts after the end of the run. So every 12 hours, we write a restart file, and then the next day we will start from this restart to do the forecast from the restart. Okay, so restart, blah blah blah, and this, yeah, with this moddef and restart, you can do some basic runs. Like if you want to have a constant wind or something very academic, you can define that in W3 shell. And then, so the next step is to run the model with W3 shell and define the some parameters for the run in the shell.inp file. So that will contain information on which forcing you need. So are you going to use water levels, currents, wind, ice, or other things? What time do you want to start? What time do you want to finish? What kind of output do you want? So here it says there's 6 type of outputs. And actually, if you use coupling, there's a 7th type of output, which is the coupling variables. And for each of these outputs, you can define a starting time of the output, an end time of the output, and then which kind of output you actually want for that type. And the 6 different type of outputs are, okay, first is the gridded output, the wave heights, the peak periods, the whatever. The second type of output is the spectra. You can request to have spectra, time series at given points. The third, I already forgot, maybe some, that the output boundary for some other models. And you can also have the restart files, what time you want to save some restart, doing some later runs. You can also request to have some full partitions for the entire grid. If you only want to have a few partitions, like the first 2 or 3 partitions, you can have them through the first set of outputs and this kind of stuff. So yeah, here they are. So grid output, point outputs, nesting information, restart files. Yeah, it used to be only up to 9, now it's up to 900 because the name of the output files will be named restart 00.w3. Then its next restart file will be restart 001.w3, restart 002, and so forth. So it's, if it goes up to 100, then it will go back to 0. So, but with 100 restart, usually you fill up your disk pretty fast, especially if it's a big grid. Because again, you have 2D spectra on the entire grid with the 4D thing, so you can write gigabytes very fast. So Wave model is a very good tool for filling up a disk. So for example, if you want to make some requests for disk space, and you need, I need a lot of disk space, so just run WaveWatch for a couple of days and get terabytes, and people say, you need the terabytes of data, I can give you terabytes of space. It's very easy to fill up the disk. So that's the basic idea of running the model. So you define the time and the output you want. It will possibly use the restart. If there is no restart, we'll just make the warning message. It will use the moddev file, and then when it runs, it will produce different output files. So a very important one is the log file. When you have only one grid, it's called log.w3, and that will tell you what the model is actually doing. So it will tell you if it's doing output, input, computation, it's timestamp, it's up to day 1 or day 2 in your simulations. So it's always good to check the log file because if you do something stupid, and it's very easy to do something stupid, then the log file will just freeze or get nothing, and then you know about it. So that's the log file. Also, of course, W3 shell will write to the standard output. And so when you run with a batch on the cluster, you typically send the standard output to some output file. So I would advise you to call it w3shell.out. And of course, you can check what is in w3shell.out because you also get some more information about what's going on. And the real result of the model will be possibly the restart files, the nest output files, the outgrd binary file, which is the file that contains all the gridded fields, so the wave height, maps, all that stuff. Same thing for the spectra. Time series, they will be in this out._pnt.w3. You can also have some output along the track. So if you want to follow a satellite and have the spectra along the satellite track, use this. Also a chip track or whatever. You can have spectra along the chip track. The idea of this special thing here is that we don't want to save all the spectra on the entire grid because it takes a lot of space. So we only do that for the restart. But then if you want to have some special setting for the spectra, you can use this track file, and we use that for the satellites to get all the spectra, all the details where the satellite does the measurements. And then you can also have this partition file if you want to have all the partitioning, all the swells for the entire grid. If you only want to have the first few swells, you can get that information inside of this outgrd file. So usually, and actually we never use this here, the partition file. Except when we wanted to use the post-processing of the tracking of the swells. But that's another business. So that's what W3 shell does. So the log file, very important. Always check what's going on here, and then the whole binary output files. And typically you need to post-process these output files for displaying, doing some plots, and looking at that. Out here the so that's a binary gridded file. So it contains different things, and you can post-process this file with W3 outf or W3 OUNF unf for the netcdf files. This is written here, or they're using the grads output if you want to use grads. And so this is the way it works for the post-processing. So here it's for outf or OUNF, it is the same. You have an input file, so here outf.inp. You get this binary file which was created by the shell. It will also read the mod.del definition file because it needs to know where the grid position are, what is the depth and everything, and it will produce the output file. So from outf, these are typically ASCII files. If you use OUNF, it's going to be netcdf files, and depending on which switch you use, you have netnt4 in your switches, and the proper environmental variables in your Unix environment, you will get the netcdf4 files. The interesting part of netcdf4 is that it supports compression. It's not a very good compression, but some compression. So typically you get a factor 2 on the file sizes with netcdf4 compared to netcdf3. The best compression is actually in the grib file, so you can also produce grib files with WaveWatch. The problem is that not so many software support grib. Too bad, because grib actually uses the same compression as for JPEG images. So each field is compressed as a JPEG image without loss. And so, grib is better, but it's less common, and so less people use it. So we tend to stick with netcdf4. And what we do is actually we store most of our data. We store the output with only 2 bytes integers. And so there's a scale factor and everything. And so most of the netcdf, like NTView, they know how to deal with the scale factors that will produce you the real values. But if you actually look at the values stored in the file, you'll see that these are integers with some scaling factor. These are just some examples of what they do at NTEP with grads by overlaying the wind variables. So there's usual methodological conventions. So we have these small things. This is a wind arrow, and the speed of the wind is indicated by the symbols here. On top of that, you have the wave direction, and the colors here, I think, are the wave heights. And this is what you find on the NTEP website. So that was the map. So the other post-processing is the point processing to take advantage of the spectral output. So from the point post-processing, you can also regenerate the source terms. So if you want to understand and make sure that the source term you computed has the right value, you can look at that. And these are the basic flow charts. So the point processing, so this is outp, but it's the same for OUNP, UNP. For the netcdf, you use this unp.inp, the binary file from the run, the mod.def file to produce your output. And this is what they play with grad. So here's also an example of spectra. And the source terms that correspond to that spectra. So here that's the wind input, the total source term, the non-interactions, and the dissipation terms. So the sum of these 3 is equal to that, and that's the trend, the evolution rate of the spectrum. And this is what you can get with OUNP or outp. And so you can also make grid files if you're working for a Met agency. And that's it. So that's track output. We don't care too much about that. Dynamic input fields. What is that about? Oh yeah, the input to the model. So the forcing. So the way WaveWatch runs, and this we had a lot of fun with the coupling with it. is that typically it's going to run 2 time levels of the forcing. So if you're integrating between 6 in the morning and 12, and you have a wind field at 6 in the morning and a wind field at 12, it will read both 6 and 12 winds and do some interpolation between. But the time step, you could also have 3 in the morning, 6 in the morning, and then 12, and then it will just adjust to whatever time you have. So you don't need to have a regular time step for your forcing. You just need to have a one timestamp for each forcing field, and then Waywatch will interpolate in time and take care of that. If you don't want to interpolate in time, you want to have a jump, you have to change the switch from WNT1 to WNT0 in the switch file to change the way that the interpolation is done. So you can do jumps, linear interpolation, some quadratic interpolation that more or less preserves the square root of a wind or some other funny things. That's all is in the manual. The only difference, the only thing where it only does really jump is for the water levels, because it's changing. When you change the water level, you need to remap the wave numbers, and that can be time consuming. So instead of doing it progressively at each time step, when the water level is updated, it does a big jump in water level, or big or small, depends on how much the water level jumps, and then it will adjust the spectrum to the new water level. All the other currents and wind, they're usually smoothly interpolated. That would be the default behavior. And so the pre-processing of this forcing. So this is if you have ASCII file, you can use prep. These days we never use it. We always use the NetDF forcing, so it's going to be RNT for NetDF files. And so you can. We had to make a few changes last time. We had a colleague from the UK had some type of levels and dimension of NetDF that was not supported. So if somehow you have a problem with your NetDF forcing, just tell us, and maybe we need to change a few things in the code to make it applicable. But we've been working with winds from MWF, ManStep, some currents from many different people. So it seems to be working, but yeah, it's never quite bulletproof. So if you have a problem with your specific NetDF files for the forcing, just tell Michael, and then we'll work on it. And and then when you do the pre-processing, so you have the input file that essentially will define the name of the input file. If it's NetDF, you will need to define the name of the variables that you want to use, because some people have some very funny names. You don't want to imagine, but currently people would call them UND. Well, guess what? People use some very funny stuff. So you need to list the names, and also you need to list the dimensions, because it's not always latitude and longitude. It can be some also very funny names. And usually when you give that to PRNT, it will be able to find in your NetDF files proper dimension and proper names and crank that. And the result will be depending, and you need also to tell if it's wind, if it's current, or if it's water level, because then the resulting file would be either a file called current.w3, a file called level.w3, wind.w3, and ice.w3. And ice is usually the ice concentration. And these days we are playing with up to 8 parameters for ice, going from the thickness to the size of the ice flows and a lot of stuff. So that's going to change in the future. So the version you have, 5.08, I think already supports the thickness of the ice, not the ice flow size yet. We're working on it. So that's a full story. So the model is going to take all these. So this is ASCII input, which tells it what to do, and then all these binary files have been produced by SCRT. And these are optional files that have been produced by the PRNT or the PREP, the pre-processing of the forcing fields. And again, it uses a ModDev file, and it will produce all these things. And then you can do the post-processing. And I think that's all I have. No, more. Nesting. Whoa, nesting. Whoa. So nesting can be nasty. Nesting can be really nasty because, I'm just going to say a few things about nesting. The old way of nesting that we used, you had to define in the parent grid, so the course grid, needs to know where will be the points on the fine grid. This is very funny. And usually you don't know. You do your Atlantic grid and you say, oh yeah, maybe I want to do zoom here. But then you need to change then you move the zoom, then you need to change the mod def for the big grid to tell it because the points are moved, so it's ugly. So I never do that anymore. So either you do multi-grid and then there are some ways to define all that properly, and we'll do that with a grid tool from NCEP to define the different grids. Or what I do, I just save some lot of spectra, and then I will use the BOUNC to put all these spectra and interpolate as I want on my grid. But otherwise, yeah, you have to be able to match the parent grid and the sun grid. And so if you're not too careful, you get some errors telling you that, oh, you cannot force with this because this point is in land or this point is in the water. And so people that have tried to do nesting with WaveWatch, they know what I mean. It can be a real pain. And so usually you have to, so you run a coarse model, then you want to try to find, of course, it's never going to work the first time. But you, oh yes, this point is in land, this point is in water, so you change it. So then you change the mask of the coarse grid, you run it again, and you go back to fine, and it's a iterative process, and usually it takes 3-4 iterations, and then you say, oh, maybe I should have used this one in the end, right? So that's a problem. That's all I wanted to say. Yep. So if there's any question about the logic of the running WaveWatch, how it works, yeah. Yes. Okay, so if you run your grid separately with W3 shell, it will never go back because essentially you run your parent grid, you get the output, and then you run the file grid. If the multi, yes, it was what I was showing before, that the both grids will be integrated in time. And what happens is that first it does the global time step of the coarse grid, and then it will do all the steps of the child grid to bring it to the same time level. Then it will do some averaging of the fine grid to push it to the coarse grid. Then you integrate the coarse grid in one step, and then you do all the steps for the child grid, you average. And so this is what makes sure that the two grids are consistent. Because otherwise we get some jumps at the edge because the waves from one grid cannot be consistent with the other one. So yes, there is two-way communication. Yeah. Okay, imagine you're running, you're an operational agency, and you have to run forecasts for the Atlantic and the coastal area of, say, France. So you then run your global model and then your coastal model, and then you put and you give your product to your users. And the people, first thing they do, speak, oh, but it's not the same thing in the two grids. What's going on here? But people won't have a consistent solution throughout the grid. So that's one thing. The second thing, for is a good reason for doing multi-grid is it's much easier to do than having to move the files around, do the post-processing, blah, blah, blah. So yeah, it makes your life much easier. Otherwise, you have to move to get all these nest files, rename them, move them around. You get crazy. Of course, when you run all the grids together, it means you can take more memory. And in some cases, there's a limit to that. So we've never integrated the triangle mesh for the French coast together with our multi-grid global system because, yeah, I think it's just going to be too big. Yep. And so actually this, yeah, I don't have it here, but what they do at NCEP, for example, they have one very strange grid, like a cloud of confetti for the Pacific. So they've cut out only the places around the atolls at very high resolution. Most of the grid is not used, but it only computes in all these small areas. And this is nested two-way in the grid of the Pacific. So this makes sure that the results that are not just Hawaii, but the Tuamotus and all the American Samoas and that stuff. Yep. So that was it. Running WaveWatch. I should stop things, right? Yo. Stop. Oh. Oh yes. Bye bye.